Hello everyone, we are going to start the new unit which is the sixth unit today and which is the thermodynamics. Okay. So first we have to understand what is thermodynamic. So thermodynamic is nothing but the branch of chemistry that deals with the exchange of heat energy into the various form and the flow of heat in and out from the system. Okay, this is called as the quantitative analysis of the heat flow is called as beta thermodynamics. Okay, everyone?
Okay, sir.
Yeah. So in thermodynamics, we have to understand few concepts related to the thermodynamic. Okay. So suppose here we have, this is the part. Suppose this all, it is the universe beta. It is the universe. Okay. It is universe. We are considering it is universe. Okay. And that small part of universe, that one I'm just highlighting that by the zebra lines. Okay, that part which is chosen for the thermodynamic study is called a system. So it is the system. Okay, what is system? System is the part of universe which is chosen for thermodynamic study is called as system. Understood?
Yes, sir.
Yeah. And here, as you can see, this is the line which separates the system from its surrounding. Okay, and that is called as surrounding. This is called as surrounding. Okay, so and system plus surrounding equals to universe. So I'm writing here universe equals to system plus surrounding. Niyati, understood beta?
Yes, sir.
Yes. And that line, okay, just I'm highlighting that with the purple line here. As you can see, this is the line which separates the system from surrounding is called as beta boundary. It is called as boundary. Okay, I hope you understood all the concept. What is system? The thermodynamic, it is the part of universe which is chosen for thermodynamic study is called a system. The line which separates the system from its surrounding is called as boundary. And the environment around the system is called as surrounding, and surrounding plus system equals to universe. Understood that?
Yes, sir.
Yes. So this is all about the concepts of thermodynamic. So here we have completed the system. Okay, what is the first law of thermodynamic? The first law of thermodynamics says the energy neither be created nor be destroyed, only it may convert from one form to other form. Okay, what is first law of thermodynamic? The first law of thermodynamics states that energy neither be created nor be destroyed, it may convert from one form to other. Therefore, the energy of the universe is constant. Is it?
Yes, sir.
Yes. Now we are going to understand about the types of system. So I'm just moving that screen aside. So we are going to understand the types of system. There are three types of system beta. One is called open system. Open system. Okay, suppose we have the cup of tea here. Okay, and we have here the hot cup of tea, as we can see here. Okay, so this is the system. Okay, and here we have the surrounding. Is it? System and surrounding. Understood? Keep
Yes, sir.
replying. So if we will observe that system, no, if you will observe that, you will see that system means the water which is used for the preparation of tea, it will get evaporate. Is it? Keep
Yes, sir.
replying. Yes. That means that system is exchanging matter from its surrounding. So it exchanges matter. And after some time, if we will observe or if we will sense that cup will become cool again. it was initially suppose 100 degrees Celsius, but after some time you will feel it is 50 degrees Celsius. Again, after some time, temperature will decrease and will reaches to the normal room temperature. That means that system exchange energy with its surrounding also. Is it?
Yes, sir.
So such system which exchange matter as well as energy with its surrounding is called as open system. So here matter and energy, okay, both exchange by the system with the surrounding is called as open system. Understood?
Yes, sir. Understood.
Now we have closed system. So closed system means if suppose you have kept, okay, covered, that is nothing but the cup of tea and which is kept covered here. So after some time you will see here that cup will become cool, but matter is going to exchange with the surrounding or not. We have covered that. Matter will exchange or not?
It will exchange, sir.
No, beta. How matter will get exchanged? Because it is covered. No, it will not going to evaporate. Will evaporate and condense inside the system only. Only it will become cool. That means energy will exchange, but not the matter. Is it or not?
Yes, sir.
Yes. So the system which exchange energy but not the matter, okay, is called as closed system. So closed system is what? The system which do not exchange matter but exchange energy with its surrounding is called as closed system. Understood?
Yes, sir.
Yes. Now we have isolated system. Isolated system, third type. Suppose that cup of tea is kept inside a thermos flask. You know thermos flask, which is,
Yes, sir.
yes. So if you will keep the, suppose the cup of tea, okay, and you will like observe after some time, is that thermos flask going to exchange matter with the surrounding?
No, sir.
No. So again here matter will not exchange. And what about energy? It is going to exchange energy? No. Because after some time, if you'll see, if you'll observe, if you'll sense, the heat will remain there only. Okay. So the system which do not exchange matter as well as energy with its surrounding is called as isolated system. So on that basis, whether it is going to exchange or not, we have three types of system: open system, closed system, and isolated system. Any doubt beta here?
No, sir.
Take a screenshot then. Take a screenshot. Done beta?
Yes, sir.
Okay. Now we are going to understand through your notebook what is given here. Wait a second. Okay. Now we have del H. Del H is called as beta change in enthalpy. It is called as change in enthalpy. So first we have to understand what is enthalpy. Any idea about enthalpy? Enthalpy is nothing but energy. Enthalpy is nothing but the energy. Suppose in any chemical reaction, okay, suppose we are having here carbon, when it burns with excess of oxygen or air, it burns and forms carbon dioxide and heat energy. Is it?
Yes,
So
sir.
it is exothermic reaction beta. If heat energy is releasing during the chemical reaction, that means heat content of that substance decreases. Suppose here we have initial enthalpy or initial energy, and here we have, let it is H1, and it is we have the after burning heat energy has been released here. So now here we have the final enthalpy, and which is represented by H2. So if we want to calculate the change in enthalpy, so change in enthalpy is represented by del H. and which is equals to final enthalpy, which is H2 minus initial enthalpy, which is H1. So the difference between final and initial enthalpy is called as enthalpy change. Okay. Suppose if it is exothermic, beta. Okay. If it is exothermic. Okay. So suppose the reaction is exothermic. For exothermic, the sign of del H is negative, which represents energy is released. For endothermic reaction, endothermic means those reactions in which heat energy is absorbed. So if heat energy will absorb, then it is positive del H. Understood? Enthalpy and sign convention for enthalpy?
Yes, sir.
Yes. If del H is constant, suppose if del H is equals to 0, if del H equals to 0, that means there is no exchange of heat energy takes place with system with its surrounding. Okay. So just do remember, if del H is negative, it is exothermic, and if del H is positive, it is endothermic. Understood?
Yes, sir.
Yeah. Next, again very important, intensive and extensive properties of a system. See, intensive means, just do remember intensive, here we have IN, so it is independent. Independent. Okay, that means those properties or those measurable properties of a system whose magnitude does not depends on amount of matter present in the system. Okay, suppose here we have beta system. Here I have taken 1 liter of water. Okay, and if I have boiled that water, so at what temperature water is going to boil 1 liter of water? Yes. Keep replying. Devanshika,
So,
at what temperature, if I'll heat that water, so at what temperature water is going to boil? At 100 degrees Celsius. Is it or not?
yes, sir.
Suppose if you are taking 2 liter of water, so at what temperature it is going to boil?
200 degrees Celsius.
No, beta, 100 degrees Celsius only.
Okay. Okay,
Is
sir.
it? Yes, because water have boiling point 100 degree, whether you take 1 ml, 1 liter, 100 liter or 1000 liter. It is going to boil at 100 degrees Celsius temperature only. Okay, that means the boiling point, melting point, density, surface tension, specific heat capacity, pressure, it not pressure, it does not depends on amount of matter present in an system. Understood?
Yes, sir.
Yes. So such measurable properties of a system are called as intensive property. Okay.
Okay, sir.
Yeah. So here we have definition. The measurable properties of a system whose magnitude or which are independent, or you can say does not depend on amount of material present in a system are called as intensive property. Okay. Like density. If you will take small water drop, or you can take a liter of bottle, or you can take 550 liter of water tank. Okay. You will find density of water will be the same. Okay, boiling point is there, melting point is there, refractive index is there. All these are, so pressure is not here. So just forget about the pressure. In your book it is given wrong, because suppose if you have balloon here, beta, suppose if you have balloon, suppose here we have 1 liter of air. If we will blow 2 liter air, that means the amount of material will increase here. It will inflate the balloon also. Is it or not? Is it?
Yes, sir.
Yes. So this is all about the intensive property. Just do repeat here. Sure, na?
Yes, sir.
What about you? Niyati, you are not replying, beta.
I am, sir. I am understanding.
Okay, okay, okay. So intensive, just do remember, see, two properties are there, whether they are depends on amount of matter or whether they are not depend on amount of matter. So for most of the time it has been confusing that whether extensive they do depend or intensive. So just do remember here in intensive we have ion, so it is independent, means which does not depend on amount of matter present in an system. Okay, but what are extensive properties? So extensive properties means those measurable properties of a system whose magnitude depends on amount of matter present in a system. Okay, like suppose we have mass. If you will have 1 kg of any material, okay, mass will be different. If we have 2 kilogram, again mass will different. That means if we are increasing the like matter, mass will increase, volume also will increase, internal energy will also increase, heat energy, even weight also, heat contain weight, because weight is also the mass dependent property. If more weight, like more mass, more will be the weight. Is it?
Yes, sir.
Yes. So those measurable properties of a system whose magnitude depends on amount of matter present in a system is called as extensive, are called as extensive properties. So here we have example, and for here intensive property I am writing more example here. Melting point, boiling point, then we have refractive index, etc. Okay, if you will take small piece of glass, refractive index will be the same. If you will take very big same glass, okay, again refractive index will be the same. What is refractive index? It is the ratio of sin I to sin R. Is it? Sin I divided by sin R equals to refractive index Ri. Is it?
Yes, sir.
Yes. So here we have completed extensive and intensive means the properties of a system. Okay, now we have the relationship between, see, del U is the internal energy. Okay, del
Sir?
H is, yes, beta,
Sir, is water a closed system?
water.
Is a closed system?
If water is present in a container, okay, suppose you are having water bottle, beta. If you are having water bottle, okay, and that water bottle is covered with the cork, then it is the closed system now. If you have water, okay, in the shallow water bottle like the steel one, okay, the isolated system, is it? In generally in cold time, like in winter season we are using hot water to drink, so we are using that shallows or Milton water bottle, okay, where if we'll keep warm water will keep warm for few hours. Is it? So
Thermoflask.
yes, yes, a kind of thermos flask. Okay, so that will be isolated system. Okay, if the water of glass is kept open at a room temperature, then it will again get evaporated here. Okay, so it will be the open system now. Understood?
Okay, sir. Yes, sir.
Yes. So here we have, if you want to calculate the internal energy or change in enthalpy, or T is the temperature, here R is the universal gas constant, and here we have del N means change in number of moles. So this is the relation between the del H and the del U. Okay, del H means the heat change in enthalpy, del U means change in internal energy, and del N means change in number of moles, and R is the universal gas constant, and T is the temperature. Okay, so this is the equation which gives relationship between del H and del U. Suppose if we are taking any reaction, okay, where number of mole do not exchange, okay, that means N1 equals to N2. Suppose you have taken water, beta, water. Okay, so water is in gaseous form or liquid form. If you are heating that, it will convert into water at gaseous form. So the number of mole will increase or decrease or will remain constant here? It will remain constant, right? Is it or not?
Yes, sir, it will remain
Yes.
constant.
So that time del n will be 0. Is it or not? You keep replying.
Sir?
That means change in number of mole will be 0.
Yes, sir.
So that time if you will keep value 0 here, so 0 into RT means 0. That means at that stage when number of mole is not going to exchange, del H becomes equals to del U. Very important. There is a conditional question are being asked, at what condition change in enthalpy and change in internal energy remains same. So you would write there, when number of mole during the chemical reaction does not change, that time del H becomes equals to del U. Understood?
Yes, sir.
Yes. And what about you, beta?
Yes, sir.
Easy, no?
Yes, sir.
Yes. Okay. So this is the first condition, you have to remember that. Now, next, the third law of thermodynamics. Direct, we have the third law. It says that at absolute zero entropy. First, we have to understand what is entropy. So suppose I have the glass of water here. Okay. So in glass of water, particles of water, they are compactly like arranged and strongly bonded with each other. Is it?
Yes, sir.
So this is the water. If I will heat that water, so water molecule will absorb energy. Okay, water molecule will absorb energy and the bond working between water molecule will lose and finally will break. And water molecule will start evaporating. Is it or not?
Yes, sir.
Yes. That means suppose I'm just taking from the solid state. Suppose here we have beta ice. So ice particles are very compactly and strongly bonded with each other. If this is ice, if I will heat that ice, ice will convert into liquid form where particles are loosely bonded with each other. Okay. And they are also not regularly arranged. This is the liquid water. If I will heat further, okay, I'm writing here the symbol of heat like this. So water will get evaporate. So water will present like this. Is it? Keep replying.
Yes, sir.
Yes. So entropy says that the randomness of particle. See here, we have increased the temperature, okay, and the randomness of particle has increased. Okay, so entropy is nothing but it is the extent of randomness of particle. Extent of randomness.
Sir, can you explain again?
Yes. Okay. You are going to school every day, college?
No, sir.
Yes, sir.
Online.
Okay, online. But before lockdown, you
Yes,
used
sir.
to? Yes. Suppose here you have the like stage for the teacher and here they are having the board. Okay, here we have the board and here your teacher used to stand. Okay, and here we have the desk bench in order to like this. Okay, in order to sit for all the students, they used to sit here, right? Suppose two students, they are sitting in each bench. So as we can see here, during the class, students are very like arranged in regular manner. Is it? Is it or not? Keep replying, beta.
Yes, sir.
Okay. So just keep your mic on and just keep replying. Again, you are muting and then unmuting. So it takes time. Okay. So keep your mic on. Both of you, Niyati and Devanshika.
Okay, sir.
So see what happens generally during the class, all the students, they used to sit in classroom very regular manner. But when the bell rang, that time student, they are wandering here and there all the time. That means here students are arranged in a regular manner. This is nothing but the extent of randomness of student. But when there is like recess or maybe the lunch time, they used to wander everywhere, right? In garden, in other class with friends here and there. Okay, so that time the randomness of student increases. Is it or not? They become not like irregular. Is it?
Yes, sir.
Yes. So entropy is nothing but the randomness of particle. Entropy nothing but the extent of randomness of particle. If particles are more random, more will be the entropy, and if particles are less random, entropy will be the less. In case of ice, entropy will be very less, and in case of gases like vapor, entropy will be more. Okay, and it is represents by S. It is represents by S, and change in entropy is called as del S. It is change in entropy. Okay.
Okay, sir.
Yes, sir.
Yeah. So now we have the third law of thermodynamics here. It says the absolute at absolute zero temperature. What is absolute zero temperature? It is 0 Kelvin. 0 Kelvin is equals to how much? It is minus 273.15 degrees Celsius. That temperature is called as beta, or it is equal to 0 Kelvin. And that temperature is called as absolute zero temperature. This temperature is called as absolute zero temperature. Understood?
Yes, sir.
Okay.
Yes, sir.
So at absolute zero temperature, entropy of pure crystalline substance is zero. Okay, that means after that particle cannot be compressed easily. They cannot be compressed at any manner. Okay, that means that particular time the randomness of particle will be zero, hence the entropy will be zero. Understood, beta?
Yes, sir.
Yes, sir.
Yes. So I hope you understood the entropy now. So
Yes,
entropy
sir.
is, yes. Suppose here we have ice. So let entropy is S1. Here we have water. So here we have S2. So if want to calculate entropy between ice and water, so you had to write like del S equals to S2 minus S1. So here that change in entropy depends on initial and final state of a system. Is it? That's why whatever the values which depends on initial and final state of a system are called as state function. Are called as state function. Understood?
Yes, sir.
Yes.
Yes, sir.
As we can see here, enthalpy is a state function. Yes, because it depends on initial and final state of a system. Hence, del H means change in enthalpy also state function, which is H2 minus H1. Okay.
Okay, sir.
Del U also, del U. See, if del H depends on initial and final state of a system, that means del U means change in internal energy is also a state function. So it is U2 minus U1. Okay. Understood, beta?
Yes, sir.
Yes. So we had again we have one more formula here. Del H equals to del U into P into del V. So here del H is change in enthalpy. Change in enthalpy.
Enthalpy.
Del U is change in internal energy. Internal energy. What is internal energy? It is the sum of all kind of energy associated with matter present in a system. It's called as internal energy. Then we have P. P is the pressure. And del V is change in volume. Del V is change in volume, and which is V2 minus V1. Okay.
Okay, sir.
Okay, so this is all about the relationship between del H, del U, and P del V. Okay, so any doubt beta till here?
No, sir.
Just do revise one more thing, one more time here, so that you can understand easily. Just do revise one more time. Now we are going to understand the relationship between del H, del U, and del N. Del N means change in number of mole. R is universal gas constant, and T is the temperature. This is very important formula. Most of the time questions are being asked. Okay, so here we have 1, 2, 3, 4, and 5 variables. So if any 4 are known, we can calculate the fifth one, right? That's why just do remember these formulas. So in the reaction, following gaseous substance like significant difference like H1, del H and del U, if VA is nothing but the volume, or we can say initial volume, and VB is the final volume, okay? The total volume of the gaseous products is Na, means the volume of gases. In the number of mole, gaseous reactant is Nb, it is the number of mole, okay, or we can say the change in number of mole. In the number of mole of the gaseous product, all the constant pressure and temperature. See, it says the temperature is constant and pressure is also constant. Then using ideal gas equation. What is ideal gas equation? It is PV equals to nRT. It is PV equals to nRT. Yes. For initial condition. For initial condition. What is initial condition? It will be PV. It is PV. It is PV equals to nRT. So for initial condition, P will be, see, it says pressure is constant and temperature is also constant. So we cannot change that. So I'm writing here P only, but V will be the one. V1 means initial volume equals to N1 into RT. Okay. For final condition, P will be PV2 into N2 into RT. Is it? So this is equation number 1. This is equation number 2. So for change in volume, okay, or can we transfer that P to other side? So we can have V1 equals to N1 into RT divided by P, and V2 will be N2 into RT divided by P. Is it? So for del V, we have V2 minus V1 beta. So what is V2 here? We have that value. So del V equals to N2 into RT divided by P minus, we have V1. V1 is what? That one. It is N1 into RT divided by P. So see here, we have common here, which is R and T and P is common. So I'm just taking that common. So del V equals to R, this constant, no? R, T, and divided by P is constant. So what we have here? We have N2 minus N1. And what is N2 minus N1? Which is del N. So del N equals to N2 minus N1. So I'm just replacing N2 minus N1 by del N here. So what we'll have? We have del V equals to RT divided by P into del N. Again, I'm transferring that. So it will be del P into del V equals to del N into RT. Understood that formula?
Yes, sir.
Yes.
Yes,
So
sir.
here we have P into del V equals to del N into RT. We have derived that. Okay. Now just we had to place that N1 into the other formula. See, here we have P into del V, and here we had one formula here, that one here. Okay, here we have P into del V. So instead of that, we can write, so we have, I'm writing here, we have, what we have? We have del H equals to del U plus P into del V. So P into del V, instead of that, can we write that here? Can we?
Yes, sir.
Yes. So it will become del H equals to del U plus, instead of P into del V, I am writing that, and which is del N into RT. So we have to represent, or we have to prove that only, and we have proven here. So it is hence proved. Hence proved. Understood, beta?
Yes, sir.
Yeah. So here we have that formula. So any doubt till here?
No, sir.
Wait a second.